Hi everyone, welcome to this presentation. My name is Trepat Borecka and I'm a doctoral student at ATH Zurich. I'll present my work solving the trend unit shunting problem using multi-agent deep reinforcement learning with routing optimization. This work is based on a master thesis that I carried out during my studies at TU Delft in collaboration with the Netherlands Railways. Our problem concerns the parking of passenger trains off the main line overnight once the day train passenger service has finished. We park them in a shunting yard, which consists of a set of parallel tracks that we are using for parking. But besides this, trains in the shunting yard have to solve a matching problem, which consists in linking arriving train services to departing train services, as well as performing service tasks, and coupling and splitting trains to modify compositions, and routing to make all this possible. This is what we know as the train unit shunting problem. So the train unit shunting problem is a hard combinatorial optimization problem faced by railway operators and is traditionally solved by hand by railway planners. But this task becomes increasingly more challenging with increased traffic and congestion in the existing infrastructure. So this triggers the interest to automatize the production of route plans. So we started with developments with operations research, but they fall too short for real life problems. So the Netherlands Railways started developing a new approach using local service, and this allowed to scale up the problems. In parallel to that, the Netherlands Railways started the development approach with reinforcement learning, which is what I'm presenting today. The main motivations to use reinforcement learning is that it can be powerful to solve real-life problems, real-time problems, and it delivers consistency of results. So what is reinforcement learning about? I'll give an overview, starting with high-level machine learning, which is the study of computer algorithms that learn from experience. So from sample data, we learn to make better decisions and predictions. We have reinforcement learning, which is a program that interacts with an environment and learns to perform a certain goal. So here we're talking about agents. The agents are autonomous computational entities that perceive information and act upon an environment by taking an action and receiving a reward based on that. So agents try to maximize the expected reward and learn to follow a deterministic policy, so which means a sequence of actions to take to maximize a reward. And this is shown in this table. So it shows the Q values or expected rewards to perform when we perform a specific action in a specific state. On the right-hand side, we have deep learning, which is a subfield of machine learning based on transforming inputs to outputs using an artificial neural network. What we are doing here is combining both into deep reinforcement learning. So the difference with reinforcement learning is that we are replacing the table that I described with a neural network. So basically the policy is represented as a neural network, and this allows us to scale up to high-dimensional problems. So the goal of this research is to incorporate knowledge from what we call the logistics side of the problem to improve routing in an existing multi-agent deep reinforcement learning framework. We are targeting different train matching problems and different shunting yards track layouts. With this information, we can help agents to learn better by guiding them to do the right movements and other decisions, and faster by constraining more the problem. I'll give a brief overview on literature. So, as I mentioned, there are classic operations research approaches in literature, but they fall short in real-life problems. There's too high computational complexity. But on the other hand, we have some approaches with the reinforcement learning for this problem, with some promising developments, although there is still work to be done here, because existing research does not guide agents to perform particular movements or decisions. The characteristics of particular shunting yard types are not accounted for. They don't make an efficient use of parking capacity, and there's no distinction between different matching problem types. I'll describe this in a minute. And lastly, we have lack of insights on the challenge of shaping rewards. Now I'll move to the methodology, and I'll start with the basic framework. So we're using a multi-agent deep reinforcement learning framework in which each agent is assigned to one train unit, and we solve this as a sequential decision-making problem. Here's a high-level overview of our framework. This is the input. So we have a set of problem instances with which we train the model. and they consist of lists of arriving and departing trains, arriving and departing times, train matching, and service tasks. Besides, we have our location and the business rules or constraints of the problem. All this fits the state of the system. So we have a set of agents that access a neural network and perform an action based on a policy, perform the action in the environment, and the state will get updated after that. For each action performed, agents receive a reward. So the focus of our work is here, the feedback that the agents receive. Now I'll move to describe the possible actions that agents can take. So we have arrival, we have movements, we have setback or change direction, combining and splitting, servicing, waiting or do nothing, and departing. We'll have as many movement and service actions as possible destination tracks. And lastly, we're using some action triggers, which are points in time created system-wide around each arrival, the end service and departure event, in which agents are prompted to perform an action. Now I'll move to describe the extensions that we developed on top of this basic framework. We developed a heuristic for random exploration and 2 routing strategies. So I'll describe briefly each of them. So training in our framework starts with agents exploring the search space by choosing actions randomly. But pure random exploration is computationally very expensive. This is why we developed a heuristic for random exploration to efficiently search the state action space based on the principles of large neighborhood search. The idea is to stimulate agents to perform certain actions. So this way we are helping them to identify patterns rather than performing exhaustive search. Secondly, we have the routing strategies. The goal of the routing strategies is to help agents to cooperate, to prevent and resolve conflicts, minimize movements, and make a more efficient use of the infrastructure. We are formulating them by means of reward functions. We developed 2 of them, the in-residence time-based routing strategy and the type-based routing strategy. And each consists of 4 components. So we have standard parking rules, combination and split rules, conflict resolution rules, and unnecessary movements rules. I'll describe briefly each of them. I'll start with the type-based routing strategy. So it consists in parking trains of the same rolling stock type on the same tracks. And we do this for problems with 0% matching. This means that departing trains consist only of rolling stock type requests. We do not specify specific train unit IDs. So in this example, with 4 arriving train services and 4 departing train services, we have as many as 10 possible combinations. So agents have to learn to solve this problem to correctly solve the instance. And this is how we park trains. So here we have a simple shunting yard with 3 parallel tracks, open on both sides. We have a gateway track on the right side. On the left side, we have a relocation track. And we have 2 different rolling stock types. And as we can see, on each track, we only have 1 single rolling stock type. So that's what our routing strategy with the rewards is trying to prompt. Secondly, we have the in-residence time routing strategy. In this case, we're sorting trains according to their position in the departure sequence. So in order to do that, we need to know exactly what train unit ID will perform each specific train service. And that's why we are using problems here with 100% matching. So as I show in this example, this means that departures consist of specific train unit IDs. So in this case, it basically means that the matching problem is already given. So it's already solved and agents have one possible solution, one single solution to solve the matching problem. Therefore, how do we park trains? As I show here in this example, there's one number next to each train parked, and it shows its position in the departure sequence. So as you can see, if all trains depart in this sequence, we'll have no blockings, which is what we try to prevent. Now we can move to the numerical experiments. We're using 2 different case studies. The first is the shunting yard of Heerlen. It's a carousel shunting yard, which means that tracks are open on both sides, and we do not have flow pattern constraints in this case, which means the tracks can be used in both directions. By contrast, in Klein-Binghorst, our second case study, we have flow pattern constraints. This means that tracks are preferably used in one single direction, as I depict in this figure. Here's an overview of the experiments. The goal of our experiments is to show the performance of our developments So for this, we developed the first experiment in which we assess the performance of our routing strategies with respect to a baseline variant. So this means baseline variant without our routing strategies for both 0% matching, 100% matching, as I described previously. And then we have two more experiments meant to show the performance of our implementations for different problem designs, different shunting yards with and without flow pattern constraints. And we are benchmarking this against HIP. HIP stands for Hybrid Integral Planning, which is a local sales approach developed by the Netherlands Railways to solve the problem. I do not have time to go into details with the experiments, so I'll give our key findings. For computational results, we have an improvement in the number of instances solved when we add the routing strategies in the framework. So we go from less than 10% to 30, 55%, depending on the problem. When we do not solve the problem correctly, it means that we have violations, and that still happens quite often. It means that agents are unable to solve conflicts or just to resolve the problem correctly. The value iteration algorithm that we are using seems to converge faster in the residence time routing strategy. This is because in this routing strategy, as I said, the matching is already given. So agents have less options to explore, and it helps them to explore faster and converge faster compared to the type-based routing strategy. And lastly, the yards with flow pattern constraints are more difficult to be solved by agents. We have a difference in the amount of instances that we are able to solve. In terms of performance metrics key findings, I'll focus mostly on number of movements. So when we add the routing strategies to the framework, we see a significant reduction in the number of movements. And we also see differences on how the parking capacity is used. So the type-based routing strategy makes a more efficient use of the parking capacity. For us, this means that we are using on average less tracks simultaneously, but at a greater length. And we see less differences when the environment is more congested. And lastly, regarding the benchmark with HIP, it's difficult to retrieve solid conclusions because the way movements are handled is quite different in both approaches. For the sake of clarity, here is an example of a route plan produced for client main course. So we see on each row a sequence of tasks that each specific train unit will perform in time. And for visualization purposes, I'll show one specific example. We have this train that arrives at the shunting yard at a specific time and moves to the service facility where it will get serviced, then move to the relocation track where it will change direction, then move to a parking track where it will wait until shortly before its departure time when it will leave the shunting yard. Lastly, in conclusions, the main contributions of our research are first a heuristic for random exploration in the framework for the problem based on the principles of large neighborhood search. And secondly, the formulation of two routing strategies for the problem in this framework by means of reward functions. So it has shown that appropriately defined reward functions can guide agents to take the right sequence of actions. And both approaches show the potential to improve the learning process and to produce more efficient route plans. The third contribution is two real-life case studies in the Netherlands railway network. So in conclusion, we have shown this approach has practical benefits to support railway planners to solve planning assignments in real time. And also that our approach with multi-agent cooperative tasks can be adjusted to solve other sequential decision-making problems in the field of transportation and logistics. And lastly, we have a few recommendations. We have first scaling up problems to real-life scenarios, adapting the routing strategies to other types of shunting yards, and lastly, incorporating crew scheduling to the problem. So that's it. Thank you very much for your attention.